Testing, testing, 1, 2, 3, testing, testing. Good. Sounds like everything's operational. Excellent, excellent, excellent. Cool. Good afternoon, Fancy Meat Computers. Hope everything's going well for you this afternoon. It seems like it's a pretty good day, so can't complain. Can't complain too much about it. So, before we get into our lecture material for today, which is going to continue on from the Topic 2 material, the mathematical preliminaries, we're going to... I'd like to talk... Yeah, it's like only mods. You've heard of OnlyFans? Well, this is only mods. So, anyway, I wanted to go over a few things before we get into our lecture material. So first of all, I'm not sure if we mentioned this since the last lecture, but we have, by popular decree, overwhelmingly the majority vote was for Thursdays at 10:30 for the virtual section. So let it be written, so let it be done. Furthermore, for virtual office hours, this is how I've decided to do this. We're going to do it at the same time as my regular office hours, but I'm going to extend the slot to 2 hours. So it's going to go from 1:30 to 3:30, and I'll have my computer open, and I'll be doing I'll be taking virtual questions at the same time as MeetSpace questions. So there you go. And furthermore, I received an email from an anonymous student after yesterday's lecture, asking for some additional resources in case you're having some trouble with the set theory stuff. So I couldn't really dig out much in the way of practice problems, but why is this cut off? Stupid. Let me see. Can I read it at least? Yes, thank you. So, so basically, rather than create problem sets, which is super labor intensive, what I've done is I have asked the textbook what the textbook thinks, and the textbook said, well, if you're looking for more information, there are a few books I would recommend. Number one is Paul Halmas's Naive Set Theory, 1960. Right here. So, you can get a reprint of the 1960 edition for $15. This is that is this. It's, not terribly, it's not hardcover, but it still works pretty well. It's got all of the stuff in it. It seems to be a really, really good book, and I'm kind of mad that I didn't know about it before. So the approach that is taken in Naive Set Theory is to approach set theory from the perspective of someone who's trying to guide themselves mathematically via sort of real-world intuitions, which is, the way that most people try to learn math to begin with. So, it's kind of in a bit of a verbose style as compared to many other textbooks that you might encounter, but this is not necessarily a bad thing. It takes a little bit longer to say things, but it also, gives you the benefit of, examples and that sort of thing. So, yeah, it's really good. I recommend it. I think, for a computer scientist, having a book like this is probably almost essential. I don't know what your textbook was for 2LC3 or 2FA3 when you did it, but I just really like it. I think it's really good. I read the first section and I was like, wow, this is really good. So I recommend Naive Set Theory, Paul Halmas. The one thing about it is that they're using probably it was a convention from the 60s when the book was written, but they mean, what's it called? Set inclusion. This is a subset of that. They take that to mean subset equals in modern parlance. So in modern sense, we distinguish subset and strict subset by having a line underneath, where the line indicates equality, which means that it's, a subset. But if there's no line underneath, then it's a strict subset, which means it's a subset and not equal to. In his case, subset it's reflexive by default. So that's kind of a minor thing, though. Otherwise, the book is very good. But yeah, you also have a couple of other ones. These other ones are you would read like the first chapter or two to get what you need. And they're very big books that are worth like $100. So, you know, I don't see why you would need them if you had this. But yeah, anyway, so if you're looking for some extra resources, some extra reading, there you go. There you go. I can attest to the quality of the Halmas book. So, yes, and anyway, so that is it, except for the fact that I got you guys the links a little bit late today, which I apologize for. I thought I had already posted them, and I hadn't. Which is, you know, it's like, oh, I wonder why there is literally nobody showed up for my lecture. Oh, wait. Yeah, so that's how that went. Yeah, so... yeah. So, might as well continue on from where we were before, then. So we were talking about relations and properties of relations, and we were just about to get into preorders and partial orders. Yes? I think so? Good. Yeah, we had talked about closures, and we were on to preorders and partial orders. So, preorders and partial orders. Let me start off by talking about the usual ordering that you would typically find over something like the integers or the natural numbers, right? So this, like the general inequality ordering that everybody learns in elementary school, this is what's known as a total order, right? So you can get to preorders and partial orders kind of two ways conceptually. You can either start from relations and build properties into them until you have preorders and partial orders, or you could start with something that you know is an order already and take properties away from it until you are left with partial and preorders. Okay? So, I'm going to try to do both at the same time, probably inadvisably. So, if a binary relation R on S is both transitive and reflexive, we call it a preorder on S. Preorders will either use the angle brace less than equals or the square brace less than equals to indicate a preorder. So, according to the apparently modern convention, if you have a line underneath, that means you're including the case where the two are equal to each other, right? If you do not have the line underneath, then what you're effectively saying is S is less than T and S is not equal to T. So, just to remind ourselves, reflexivity is the property where if you have this relation, relation S is in there, right? So if you're talking about the normal ordering over the natural numbers, 5 is less than or equal to 5. 7 is greater than or equal to 7. So that, that's fine. Good. The other thing is transitivity. So we can say if A is less than B and B is less than C, then A is less than C. Right? So, and this is less than or equal to, right? So you could say, if 3 is less than 4 and 4 is less than 5, then 3 is less than 5. That is a property of the normal total order, and it is also a property of preorders. But interestingly, you don't get any other properties besides transitivity and reflexivity. in order to get to partial orders, you must include the property of antisymmetry. So remember, the property of antisymmetry is if I have A is less than or equal to B, and B is less than or equal to C, that, sorry, no, that's transitivity. Pardon me, reverse that. A is less than or equal to B, and B is less than or equal to A. I wish I had a chalkboard. I should open up a notepad thing. Get it. Examples. All right. Here. This will do. So if A is less than or equal to B, and B is less than or equal to A, the implication is that B and A are the same thing. A and B are equal. This is the property of antisymmetry. So if you think about that, it makes sense. It makes sense in the case of the total ordering, because 4 being less than or equal to 7 and 7 being less than or equal to 4 would imply that 4 and 7 are the same thing, which, of course, is not the case. So there you go. That would only be the case if you had, like, 5 is less than 5 and 5 is less than 5. Obviously, in this case, since we're mapping onto natural numbers, 5 is equal to 5. There you go. Yeah, I do need a drawing tablet. Man, it's just, like, endless things you can buy for streaming, eh? To be honest, like, the second monitor is actually really, really helpful. Because now I don't have to worry about, like, it always seemed unprofessional to me that I would have, like, OBS ever, like, displayed to you guys. That, you know, it's just, you watch a professional stream and you never see it, you know? And I can always just, like, pop it in, pop it out. There we go. Anyway, so once you add that property of antisymmetry, you're now talking about a partial order. Yeah, so, yeah. Yeah, well, the thing I was saying was before was wrong, right? False, yeah, so if you do 4 is less than 7 and 7 is less than 4, like, this one's false. Anything in false is, like, it can't be true. So there you go. Screen mirroring script. Interesting. That would be cool. We'll talk. Well, I don't have a tablet. You know what? Whatever. We'll see. Anyway. So, another way of thinking about this is to take the total order over the regular numbers and remove properties from it until you get back to pre-orders and partial orders and then pre-orders. Parenthetically, it's sometimes easier to think of a pre-order as being something like more like a graph than a something more like a graph than a regular order. Yeah, that's true. Oh yeah, so yeah, 4 is equal to 7. Yeah. Sorry, pardon me. Yeah, so if 4 is equal to 7 is false, so false does imply false. So I'm still not wrong. But you know, false implies everything. So, like, anyway, we're gonna get into it. I see you guys have a firm foundation in propositional logic. So, yeah. So, total orders. We know of a few sets over which, like, we have a defined total order, right? So natural numbers, integers, and real numbers, we already know what orderings are intuitively, or, we spent a certain amount of time in elementary school already learning what this is. So this is a total order. I have referred to it that way several times. The particular property that turns a preorder into a total order, which is like kind of the tricky one conceptually, is this idea of strong connectivity or totality. So in addition to being transitive, reflexive, and antisymmetric, for all S and T in S, either S is less than T or T is less than S. That is to say, every pair of elements in S is related by the relation, the regular inequality relation. So the thing that differentiates a total order from a partial order is this totality property. In a total order, pick any two elements out of the set, and you have a defined relation between the two of them, right? Another way of saying this is that if you construct the set S times S, or S cross product S, each one of those is either in SRT or TRS, right? So every one of those tuples is going to be in the relation. If you pick 7, 7 is always less than everything that's above it and greater than everything before it. The difference with a partial order is that 7 might not be less than or greater than 11, for example. So this kind of gives it more of a. It looks more like a graph. You guys have done graphs, right? You guys did graph theory? Hopefully you guys did graph theory. I'm bleeding. Picked a scab. Have you guys done graph theory? Wow, 50-50 at 20 votes. Okay, okay, so graph theory. Okay, I don't have any slides. Well, I don't have any slides in. Yeah, if you did graph theory anywhere, you would have done it in 2MD3, I think. Although it was possibly also touched on in an algorithms course. All right, I have some slides from some course somewhere about. I have a few slides on graph theory, which provides a very rough intro to it. So I'll pull those up now, since about half the class has no idea what I'm talking about. Yes. Once I show you this, you'll probably be like, oh, yes, that. Absolutely. So, brief introduction to graph theory. Okay. So, this will actually make a little bit more sense now that we're talking about now that we've done some foundations of set theory. This will actually probably be a pretty good introduction to graph theory. But all right, so graphs. All right, graphs are super useful, and it's an abstraction that's used throughout computer science to model various types of computations. If you, like, I'm assuming you guys have heard of the traveling salesman problem, right? The traveling salesman problem is in, the traveling salesman problem is a graph problem. Yeah. So, okay, so all I have to do is, like, show you guys this stuff. Okay, we'll go through it anyway. It's only 4 slides. So, a graph is a way of modeling the relationship between objects. So, it maps onto a lot of stuff, right? A graph is defined mathematically as the ordered pair G is equal to V, comma, E, where V is the set of nodes or vertices, and E is the set of edges conforming to E being a subset of X, comma, Y, where X and Y are in the set of vertices, and X does not equal Y, right? So, yes. So, basically, a graph is basically a carrier set paired with a relation. Like the relation E, you can think of E, the set of edges, as being a relation, but I find it actually works quite well in the reverse, because graphs are, like, normally, like, they have a much clearer visual representation. So if you think of something like a preorder or a partial order as being a graph with certain properties, it actually, it works a little bit better in the brain, I think. So, let me just close this poll. There we go. The above means that an edge is defined as a pair of vertices where the two vertices may not be the same. Yes. So, although in some graphs you do have self loops. So, here is an example of a graph with vertices 1 through 6 and edges 6, 4, 4, 3, 4, 5, 5, 2, 2, 3, and 2, 1, and I think I did 5, 1. There you go. Right? So, is DC3 the Java course? I don't know. I didn't take these courses. My second year course is mechatronics. I'm not really involved in the second year computer science people thing stream. So anyway, so that's an example of a graph. The previous 2 slides present graphs in their most general form. If we apply properties to graphs, we get some interesting structures. Directed graphs. So if the ordering of the numbers in an edge pair matters, then the graph is directed. Simply put, graphs have arrows. The graph will have arrows instead of straight lines. And then we have the property of cyclic versus acyclic. So, a graph is cyclic if it contains cycles, and if it's possible to return to any node by following the edges of a directed graph, then it is cyclic. Otherwise, it's acyclic. So, this is a directed cyclic graph. This is a directed acyclic graph. How could this possibly be relevant to programming languages? Remember when we said abstract syntax trees? Well, programming languages are arranged as trees. So there you go. This is relevant. Graphs have a lot more properties than this, but this will do for now. So yeah, and then it gets into, like, the actual subject of this course, which is C programming. So that's what a graph is. So think, when you have a preorder, right? Let's say a good example of, I think, a pre-order is Pokemon types. So think about the Pokemon type matchup system. Okay, that might not make a lot of sense to anybody who's not played a Pokemon game, but if you've never played a Pokemon game before, Pokemon have elemental types, and these types have advantages and disadvantages against other types, and, like, memorizing the type matchup chart used to be a central element of the strategy in Pokemon games until they just got the game to tell you what the type matchups are, thus ruining every piece of good strategy that there was in a Pokemon game, and everything since that they made that decision has been utter trash. But, quality of life improvement, my ass. But anyway, so, fire is good against grass, grass is good against water, water is good against fire, right? So these things, you can do these as a graph, right? But these are also, like, consider all of the types in Pokemon to be elements of the set, and the, what beats what to be the pre-order over them. So, yes. Although without the property of transitivity, because if fire beats water, if water beats fire and fire beats grass, that doesn't mean water beats grass. So there you go. Yeah. So anyway, like, that's the type of thing that you should be thinking about with this. Okay. Okay. Are there any questions about pre-orders or partial orders? Pre-orders, partial orders, total orders. Yeah. Yeah. So the trick, though, like, from the perspective of a like, there's knowing what a graph is and being able to work with one computationally is one thing. Knowing what a graph is and being able to work with it in shut up, me. Being able to work with it in the form of mathematical abstraction, which is what will be required for this class, that's like a whole different thing. So, you gotta be able to do both. You gotta, when I say graph theory, you need to know what I'm talking about. So, joins and meets. If less than equals is a partial order on S, is Boolean an order? No. Boolean is not an order. Boolean arithmetic is more like an expression system, which is what we're going to be talking about in our next set of lecture slides. So, if less than is a partial order on S, with S and T elements of S, then J as an element of S is the join, or least upper bound, of S and T if S is less than J and T is less than J. And if for any element K, if that property holds, then J is less than or equal to K. So, yeah, so Boolean truth values is the set. Well, it's not really very, like, normally we don't define an ordering over the Booleans. We don't say that true is greater than false. Although, that might to say that true is greater than false is you're no longer in the realm of logic. You are now in the realm of philosophy and religion. And it is not our objective to teach philosophy or religion. It is our objective to teach logic. So false and true are not, there is no ordering relation between them, at least in the conventional sense. So, the join is the least upper bound. It is the smallest number such that it is still larger than both S and T. Similarly, the meet, or greatest lower bound of S and T, is some element m such that m is less than both s and t, and yet still greater than all of the other elements, greater than or equal to all of the other elements that are less than s and t. Oh man. So, okay, Mark. All right. Equality relations are not anti-symmetric, they are symmetric. I'll give you reflexive and transitive. But yeah. But no, equality, generally speaking, is symmetric rather than anti-symmetric. Because, you know, to say x is equal to y and y is equal to x is the same. In fact, that's how we define an equality. That's how we define an equality relation, is that it's reflexive, transitive, and symmetric. So, chain of fools. Suppose we have a preorder on S. A decreasing chain is a sequence of elements of S such that for every I is... oh, whoops. That should be I plus 1 with the subscript. Shoot. And here I was saying how it was so awesome that everything was... my goodness. There we go. Compile that up. That's how it's supposed to be. Ta-da! Yeah, there you go. Math! Ha ha ha! So yeah, there you go. So basically every element must be, if it's a decreasing chain, every element has to be less than the one that went before it. So chains can either be finite or infinite. A set with no finite decreasing chains is said to be well-founded, and a set with infinite decreasing chains is not well-founded. So if it's got an infinite decreasing chain, basically the analogy is that you can draw an analogy by mapping it onto the integers, and if it's a well-founded set, you can draw an analogy by mapping it onto the natural numbers, because the natural numbers stop at 0. There is no element less than 0. So basically, the idea is if you have the numbers that are like, the thing about preorders and partial orders is that you can have several of these decreasing chains existing in the same set. Because you don't have the property of totality, you can have like disjoint networks. Like you can think of them as disjoint graphs all within the same set. They don't necessarily have to be all connected, right? That would be another property. So, you know, distinct decreasing chains can exist within the same set, so long as there's no infinitely decreasing chain inside of there, then the set is well-founded. It can have multiple decreasing chains, so long as they're all well-founded, then the set is well-founded. Cool. All right, proof by induction. We're going to talk about induction now. This is proof by induction. If you object to my conjecture, I'll put you inside this coil of wires that'll create electrical eddy currents in your body until you vaporize. Professor Schmidt demonstrates the concept of proof by induction. Proof by I think that we would consider that a coercive proof. So we're gonna have to induce. Wait, before we get there, Are there any more questions about relations before we move on? Gonna assume no. When I ask for questions and you don't have any questions, just give me a thumbs up. That'll be our thing. That'll be our thing in this class. So, induction. Will the content of this lecture be sufficient to finish assignment 1? Yes. Yes, it will. Yep. Yes, the content of this lecture is sufficient to finish assignment 1. Is there a Venn diagram showing relationships between orders? I mean, you could easily make one, you know? But, you know, I'll leave that as an exercise to the listener. So, although that's a good idea for, like, later inclusion in the slides. So, anyway, principle of ordinary induction on natural numbers. This is the principle of induction. Hopefully you will have heard of this before, especially in 2FA3. But, again, there's a reason we're going over all this. Principle of ordinary induction. Suppose P is a predicate on N. We take as axiomatic that P at 0 and for all I elements of N, for all I, that should be an exists, actually. Yep, that should be an exists. Sorry about that. Jeez. Here I thought that this was... Ay, ay, ay. Let me just fix that very quickly. Bloody hell. Okay. Well, okay, so what does the textbook say? Like, was that at my insertion or what? This is important. This is an important thing to get right. Yeah, it's for all. For some reason. Pardon me. I guess I'm just, I'm getting jumpy. I guess the thing about for all is, like, normally it's sufficient to make I a variable and then, you know, prove it for that. I guess I'm just confusing myself. Just confusing myself. Yeah, it's for all because it needs to hold for the entire set for the induction to work. Yes, this is true. It is, yeah. It should be, yeah. You guys are right. I'm just confusing myself. I shouldn't double check. I shouldn't double guess or second guess myself. So, anyway. For all I elements of N, if Pi implies Pi plus 1, that implies that for all N, Pn. So, an induction. You get the base case, you get the inductive step. In other words, if we can establish the base case of P at 0, and that Pi p of I plus 1 is a necessary consequence of p of I, we can conclude that p holds for all the natural numbers. Yes, thank you. So, for example, the following argument follows the above structure. Premise: you were completely lost in this class in the first week of class. Premise: for any week of class, if you were lost in the last week, you will be lost this week. Conclusion: you will always be lost in this class. Now we'll do the principle of complete induction on the natural numbers. As your colleague has pointed out in the chat, this is also known as strong induction. So, if for each natural number n, it is given that pi holds for all I less than n, and that this demonstrates that p holds for n, we may conclude that p holds for all n. In other words, if you have p at 0, well, if you have p at 0 and p at 1 and p at 2, 3, 4, 5, 6, etc., all the way up to n, implying p at n, that implies for all k in n, p of k. So there you go. This p is implicit there. So there you go. So, complete or strong induction is so named because it uses a stronger hypothesis than simple induction. So, there's this interesting property that you have in mathematics where kind of the stronger your hypothesis is, the easier it is for you to prove. Think about how much you have to work with when trying to produce these proofs, right? In the case of ordinary induction, you can hypothesize only the previous step to get the next step. In this one, you can hypothesize everything in between, like everything from 0 all the way up to, 1 minus the thing you're trying to prove. So that's the difference. You can, because it's an equivalent method, actually one can be derived from the other. You can use either of them. A lot of the times in this course, for our purposes, we will be using strong induction because it's a little bit easier to get a proof together because it, again, you get that much more to work with. So, here's an example of complete induction. Premise: you were lost in this class for all weeks prior to a particular week. Premise: being lost for all weeks prior to a particular week implies that you are lost in that particular week. Conclusion: you will always be lost in this class. So, a numerical example. This is probably one that you guys have done before, but again, we'll just go through it. Consider the fundamental theorem of arithmetic, which is, a pretty bold claim, fundamental theorem of arithmetic, but here we go. Every natural number greater than 1 is the product of one or more prime numbers. So, this is what we're trying to prove. We're trying to prove every natural number greater than 1 is the product of one or more prime numbers. We can prove this using complete induction. Base case. In this case, we are concerned with the natural numbers greater than 1, so our base case will be 2. Is 2 the product of prime factors? The only two factors of 2 are 1 and 2. The definition of a prime number is a number which has no factors other than 1 in itself. Therefore, 2 is a prime number. This argument also applies to 1. 1 is a prime number. 1 and 2 are prime, therefore 2 is the product of prime numbers. There you go. Well, people might argue about whether or not 1 is prime or not, but, So, there you go. So now let's attack the iterative case. If n, which is an element of the natural numbers, is prime, then it is trivially the product of a prime number and 1. So, to attack the iterative case, we're breaking it up by cases, right? So the first case is n is already prime. So if n is already prime, then we're done. Otherwise, n has 2 factors, which must be less than n, because less than or equal to, well, it must be less than n, because the only multiplication which yields a number where one of the factors is the same number is when you're multiplying by 1, but we've already considered that case. It doesn't get us anywhere. So, if m1 and m2, if it is given that m1 and m2 are prime factorizable, that is to say, m1 is equal to p1 times p2 times whatever all the way up to pk, and m2 is q1 times q2 all the way up to qj, that is to say, m1 and m2 are the product of a series of prime numbers, where pi and qi are prime numbers, then we may say that n is equal to p1 times p2 all the way up to pk times q1 times q2 all the way up to qj. Therefore, n has no factor which is not prime, since primes are irreducible. We got this hypothesis from our inductive step. There we go. How can you just say, if it is given that m1 and m2 are prime factorizable? Yes, that's the induction hypothesis. So we get that because, according to induction, we get to assume this bit, right? We get to assume this, and we need to demonstrate that it proves that, right? That's the power of the induction method. That's the power of the induction method. It suggests to you what your hypothesis should be. So, to demonstrate this implication, all we need to do is we need to take these premises, assume that they're true, and then following some either deductive steps or algebraic rearrangements in the case of something that's algebraic, then this is how you produce it. Yeah. So yes. Where So n has no factors which are not prime, since primes are irreducible. Therefore, n is the product of prime factors. Q, E, D. So, question. Is this an example of a formal or an informal proof? This is a formal proof. Just because it's a formal proof does not mean it needs to be written explicit. Just because it's a formal proof doesn't mean that it needs to be written entirely in mathematical in mathematical equations. The mathematical formulae are representative of arguments, right? We can make the arguments using natural language as well. Like if you actually go through, if you go through and read the textbook, like many of the arguments that they present are presented in explicitly this style. So yeah, for those of you who have been wondering how to perform the assignment 1 questions, which incidentally, like this week is the proper week that you should start working on them, like according to where we are in the lecture material, then this is an acceptable solution. This goes against what I thought they told you in 2FA3. Well, okay, so how did they define it in that 2FA3? So you shouldn't think about like formal and informal proof as being so much like black and white categories. It's more um, like your proof will have a level of formality, right? Um, just because this particular proof has been done primarily using spoken English, that doesn't mean that the logic is any less formal underlying it, right? Mm. Okay, so here are some definitions. A traditional proof is an argument for some intended audience expressed in a stylized form of natural language. A formal proof is a derivation in a proof system for a formal logic. Ah, yes, okay. So, well, hmm. It just depends on what, like, you consider the proof system, right? For this particular example, like, we're pulling in, you know, elements of propositional logic, we're pulling in elements of arithmetic laws, you know, there's no step here which is not founded in logic, even if it's not precisely using, like, I haven't formulated it in the form of, you know, a sequent. But, you know, that can be, like, my position is basically that that's not necessarily material to the underlying argument, right? Whether or not the argument, like, the argument is, like, the logical propositions themselves are the logical propositions, regardless of whether they've been expressed, you know, in natural language or in formal mathematics. Obviously, formal mathematics has its advantages and its disadvantages, and natural languages has its advantages and disadvantages. But yeah, like, I don't know. Maybe I have a. Let's see what we think. Hmm. Hmm. So you guys think that a formal proof is something that you should be able to feed into a computer, or at least one of you thinks that. Um. We're kind of over time, but this seems like an interesting point, so I think we should hash it out. So. If we have an induction step, assuming Pn equal the... So, yeah. Well, that's true. Am I talking about formal or rigorous? Hmm. I guess it's my position that those are pretty much the same thing. Yeah. Like to me, like, whether or not you're dealing with like, whether or not the proof is like the level of formality is like related like to the semantic content. Yeah, it's basically it would seem that the position I'm arguing is basically the syntax doesn't matter. What matters is the underlying semantics. I don't think you can attach an image, but yeah. Yeah. Ah, okay. I think that perhaps the difference I'm having here is the difference between it being in a formal language and being formal language, right? That is to say, rigorous. So, yeah. Yeah, it seems like this is going to be this class. A lot of, you know, arguing in this manner. Yes. So all right. If somebody wouldn't mind emailing me Dr. Farmer's slides, that would be I would find that interesting. The slides that we're referring to here. Okay. Well, at any rate, I think that'll do for today. I'm sure a lot of you have to run along to class, so thank you. We'll resume this tomorrow, and maybe we'll sort these things out. But you know, the long and the short of it is the type of proof that like when in assignment 1 when I'm asking you for proof. To prove various things. I'm asking you to do it more in this style. So, you know, make sure that it's rigorous and well-reasoned, but, yeah. I don't think that traditional and informal are interchangeable. Like, traditional... Maybe it's informal. Like, again... Like, level of formality in my view is not, it's not like an on and off switch. It's not like in theory, if you express the proof in a language in which you are incapable of informality, then by expressing the argument in a language in which you cannot be informal, you are by default formally expressing the language, but that doesn't mean that that's the only way to do it. Right? Well, yes. Yeah. Well, obviously all traditional proofs would be written in formal or in natural language, but that doesn't mean that the only things written in natural language are traditional proofs. Right? Like, you know? I guess it's like, am I making the assertion that you can write a formal proof in natural language? You know? I don't know. I feel like we're getting into the weeds here a little bit. Take her easy, folks.